For years, warp drives were treated as an interesting idea that couldn't exist in reality, mainly because they required forms of energy we've never observed. That assumption is now being challenged. A new peer-reviewed study proposes a warp drive model that works within known physics and does not rely on negative energy. While this does not mean faster than light travel is achievable anytime soon, it does change how scientists evaluate warp concepts. In this video, we will examine what the researchers actually found, what it means scientifically, and what it doesn't. Let's get started. The recent announcement is based on a peer-reviewed theoretical study published in Classical and Quantum Gravity. The paper presents a new class of warp drive solutions that remain fully consistent with Einstein's general theory of relativity, but without relying on negative energy or exotic matter. To understand why this matters, it's important to focus on what the authors changed. Traditional warp drive concepts, including the famous Alcubierre drive proposed in 1994, describe a spacecraft enclosed in a warp bubble, where space-time expands behind the ship and contracts in front of it. This allows the bubble itself to move faster than light relative to distant observers, even though the spacecraft inside never locally exceeds light speed. The problem was always energy. Alcubierre's solution requires enormous amounts of negative energy density, something that has never been shown to exist at macroscopic scales. Over time, this requirement led many physicists to treat warp drives as mathematically interesting, but physically unattainable. The new study approaches the problem from a different direction. Instead of focusing on moving a spacecraft through space-time, the authors examine whether self-consistent space-time structures can propagate in a controlled way using only positive energy densities. In other words, the emphasis shifts from transporting an object to engineering the geometry of space-time itself. Their equations show that such space-time configurations are mathematically allowed and do not violate known energy conditions. The result is a model sometimes described as a physical warp drive, not because it can be built today, but because it no longer depends on impossible forms of matter. Importantly, this model describes constant velocity, subluminal warp motion. It does not exceed the speed of light. That distinction is central to understanding what this research does and does not quite claim. The real significance of this work lies less in speed and more in legitimacy. For decades, warp drive research carried a built-in disqualifier: the need for negative energy. That requirement made it easy to dismiss the entire concept as incompatible with physical reality. This paper removes that automatic barrier. By demonstrating warp-like space-time motion that satisfies standard energy conditions, the authors show that general relativity itself does not forbid such structures. This repositions warp drives from the category of forbidden physics to extreme but theoretically allowed. That shift has meaningful consequences. In physics, removing a fundamental impossibility often opens the door to serious exploration, even if practical implementation remains distant. Once a concept is shown to be physically allowed in principle, it becomes something that can be refined, tested mathematically, and challenged through further research. Another important aspect of the paper is its conservative approach to causality. Because the model remains subluminal, it avoids the paradoxes typically associated with faster than light travel, such as violations of cause and effect. This makes the solution more stable within the framework of known physics. The work also reflects a broader trend in theoretical research over the past decade. Several studies have attempted to reduce the energy requirements of warp metrics, improve their stability, or reframe how spacetime manipulation might occur. This new model brings those ideas together into a coherent framework that can be systematically explored. The peer-reviewed context matters as well. Classical and Quantum Gravity is a well-established journal, and publication there signals that the mathematics and assumptions meet accepted scientific standards. While not all physicists agree on the interpretation or implications, the work is taken seriously within the field. In short, the scientific importance of this study is not that it delivers a warp engine, but that it changes the question from "is this impossible?" to "how difficult would this be to realize?" Despite some headlines suggesting otherwise, this research does not mean warp travel is close at hand. The engineering challenges remain overwhelming. Even without negative energy, the space-time configurations described in the paper require immense energy densities, precise gravitational control, and levels of technological sophistication far beyond current capabilities. The gap between mathematical models and physical construction is still enormous. Another key limitation is that this model does not enable faster-than-light travel. While it demonstrates warp-like behavior, it remains constrained by the speed of light. This may seem underwhelming, but from a scientific perspective, it is one of the model's strengths. It aligns cleanly with relativity and avoids unresolved causal problems. So why does this still matter? First, it reshapes how interstellar propulsion is discussed. Traditional propulsion systems scale poorly over interstellar distances. Even optimistic near-light speed travel would require journeys lasting decades or longer. Warp-based concepts represent a fundamentally different approach, one that focuses on space-time geometry rather than acceleration. Second, the work provides a foundation for further research. Once a physically allowed solution exists, researchers can explore how to reduce energy demands, improve stability, and examine whether related configurations could have more practical applications. This is how theoretical physics progresses, through incremental refinement, not sudden breakthroughs. Third, the model offers tools for simulation and exploration. The authors and others are developing numerical frameworks to systematically map warp metrics, test boundary conditions, and explore how spacetime responds to different energy distributions. Even if practical warp drives never materialize, these tools deepen our understanding of gravity itself. There are also unanswered questions. It is not yet clear whether quantum effects would destabilize such spacetime structures, or whether unknown constraints would emerge at extreme energy scales. These uncertainties are not flaws. They are the natural next steps for investigation. What this research ultimately does is provide something rare in speculative physics: a clear, testable, and physically grounded starting point. This research does not bring warp travel any closer to reality, but it does remove a long-standing theoretical roadblock. For the first time, warp-like motion appears physically allowed without exotic matter. The challenge now shifts from impossibility to feasibility.